Hello everyone. Let's do the impulse and change in momentum PostLab. So in that lab, you ended up graphing the impulse in units of Newton seconds versus the change in momentum in kilogram meters per second. And your graph was, of course, more or less linear. It's a little hard to get perfectly linear data in this lab because you're smashing things together, but still, most of your graphs are 0.99 or so correlations. It also went through 0, 0, and therefore the impulse is indeed related to the change in momentum. They are proportional to one another. Remember here that impulse is kind of a loaded term. It's a force acting through a time. So the amount of force you apply over an amount of time is proportional to the resulting change in momentum. Let's make a y equals mx plus b math model. Your y variable is, of course, impulse, and that equals your slope. Let's take a look at what we have this year, at least, up to this point. Won't be a lot of groups since this is after the seniors have left, but here we go. Here's all of our data, and you'll notice down here the average slope is about 0.99178. In other words, the average slope is within 1% of 1. So our slope is 1. Let's look at the units. Units for slope, of course, come from rise over run. So a Newton second over a kilogram meter per second. Now this may not look like it'll cancel, but remember, a Newton is a derived unit. It is based on Newton's second law, F equals ma. A Newton is the force required to make a 1 kilogram object accelerate at 1 meter per second squared. So if you substitute that in for a Newton, notice the kilograms cancel, the meters cancel, and all the seconds cancel. So essentially, this slope, or constant of proportionality, if you will, has no units. So our x variable is the change in momentum, not just momentum, but how much the momentum changed, and that's a vector quantity. And since, of course, 1 is the multiplicative identity, when you multiply by 1, you get the number back, impulse is simply equal to the change in momentum. And this is what is known as the impulse change in momentum theorem. And so there's a definite relationship. They're just equal to one another. So you apply a force through a time, imparting an impulse to an object, and that impulse results in a change in momentum. And those two things are equal to one another. So when we compare these two things in the lab, we found that they were exactly equal to one another. Now let's talk a little bit about this impulse. In our lab, we found impulse by taking the force versus time graph, which looked pretty much like the spike that we saw here and in the Newton's third law lab earlier in the year. And we found the area underneath using the computer. So the computer actually figured out how to fit this curve with little rectangles and squares and things and counted them up to figure out the area. That would be hard for us to do. And so a couple of ways we might approximate this. One is we might turn this into a triangle, in which case you could use 1/2 base times height. But the more accurate way is that instead of looking at a force which changes over time, what if we had a constant force, notice the horizontal line, which acts for the same amount of time. And that force applies an impulse, the area under this curve, which is exactly equal to the impulse that we're drawing here in blue. Notice this little piece and this little piece basically fill in this blue piece up here, right? So the areas are the same. Well, what force would do that? What force could we use as a constant that would impart the same amount of impulse? Well, simply, it's the average force. If we add up all the different forces we had and take the average over the same amount of time, we'll get the exact same amount of impulse. So the average force here is simply the constant force that imparts the same impulse. That's what averages do. Right? So they act just like they're constants that do the same thing. So the reason why we might want to do that is because we can find this area. If this is the change in the time, it's the time interval of the collision, and this is, of course, the width of the rectangle, the average force, then area is simply length times width, or force times time. So here is how we can calculate impulse as long as we're going to use constant or average forces. So that's the way we're going to approach most of the problem in this unit, given that this is an introductory level of physics. If you get into AP, you'll talk more about how to find this area under the curve, which for those of you that have had enough calculus is an integral of the force versus time function. all right, for this. But, for us, we're going to try to keep things a little simpler. So this is the kind of thing we can use. And often we're not even going to call it an average force. We'll just say the constant force times the time. So that means then we can define impulse in two ways. First of all, impulse is a capital J. I is used for other things in physics. So it's the area under the force versus time graph, but it's also the product of the average, hence constant force, and the time that force is applied. Impulse is force acting over a time. Force acting over a distance was work, right? FD cosine theta, an amount of energy transferred. So force over time is impulse, which is equal to the amount of momentum that's changed. So our impulse equation is basically force times time, and therefore impulse would have units of force, newtons, and time, seconds. So impulse would be given in units of newton seconds. Plugging that in, we then get a mathematical statement of the impulse change in momentum theorem, at least for constant or average forces, where the force times the time is equal to the change in momentum. And you'll see in the MOPs that we can think proportionally through this fairly simply because there's no squareds or square roots or fraction type stuff going on. Now, one other little comment about units. If impulse is force times time, then its units are, as we just mentioned, newton seconds. If momentum is mass times velocity, then change in momentum will have units of kilogram meters per second. Now you might say, now wait a minute, how can something which is equivalent, which is equal, have different units? Well, that's because a newton second actually can be broken down. Because as we mentioned a moment ago, a newton is a kilogram meter per second squared. Notice one of the seconds cancels, and we're left with kilogram meters per second. So a newton second is really the same units. Does that mean we can just use whichever set we want? Not technically, not if you want to be conceptually accurate here. Since impulse is force acting over a time, you need newton seconds. Momentum, mass times velocity, you need kilogram meters per second. So if you want to be accurate with your units, you have to use the set that it pertains to what you're talking about. Yes, they're equal, but you still have to deal with the right units. We've actually done that before. If you remember little g, the gravitational field strength, or the acceleration due to gravity near the surface of the Earth in both cases, we use the same symbol, we use the same number, 9.8, but we use different units. For the gravitational field strength, it was 9.8 newtons for every kilogram of mass in the gravitational field. For the acceleration, it was a negative 9.8 meters per second for every second. So that was the meters per second squared. But a newton per kilogram and a meter per second squared, you can kind of see here, are the same units. But you have to use the right units to get the right understanding. Now, one thing you can notice from the lab is that this equation held in all the different types of collisions that we had, different masses, different velocities, and different actual collisions. We actually had two types. When you were using the magnet ends, you were doing what is called an elastic collision. And this is a collision where kinetic energy is conserved. Remember, in science, conserved means doesn't change or remains the same. And so that means that there was no E-dis during the collision because they didn't actually touch with the magnet ends as long as you didn't smack them together too hard. Now, technically, you probably dissipated a little bit of energy. Okay? But if you looked at your speed on the way out, it was probably about the same as your speed on the way in. Not the velocity, by the way. It changes velocity. Right? But your speed on the way out was basically the speed on the way in when it bounced off. And so that means the kinetic energy is the same. Most collisions are not elastic. And you should never assume a collision is elastic without some evidence. Right? Most collisions are like our other ones. They're inelastic. This is a collision in which kinetic energy is not conserved because energy is dissipated. In most collisions, that's usually stored as thermal energy, sound, deformation of the objects, all these things that dissipate energy. Right, so when we use the spring plunger on the other cart, that probably dissipated a little bit of energy. Not a ton, because the spring is pretty good, but unless we assume it's an ideal, perfect spring, it's going to dissipate some energy. You could hear it, for example. When we use the clay end, it dissipated all of the energy. That would be called a completely inelastic collision. The plunger would be a partially inelastic collision. So the clay was a completely inelastic collision because all of the kinetic energy was dissipated. Right? It stopped when it hit the clay. So we have kind of gradations of inelastic collisions, but most collisions are inelastic to one extent or another. Only real elastic collisions are things like subatomic particles in a particle accelerator where they smash them together and see what falls out, are actually going to be pretty much elastic collisions. But we can approximate them using magnets, maybe billiard balls because they're hard and round so they only touch at the one little point, even though they do have some sound, which is dissipated kinetic energy. But, you know, pretty close to an elastic collision. But again, never assume it's elastic without some evidence. Now, we don't have to just be satisfied with the lab. Okay? We can also derive why those two things, why impulse and change in momentum are equal. Let's start out with constant average forces leading to Newton's second law, which says that the net force is equal to the mass times the acceleration. This is actually a modern formulation. It's not the way Newton wrote the second law in his Principia. We'll see the version that he wrote in a moment. If the net force is constant, then the acceleration is uniform, and we can write it as the rate of change of velocity. Right? It's the slope of the velocity time graph. It's the change in the velocity over the change in the time. Plug that in, and we get the net force is equal to the mass times the change in the velocity over the change in the time. But if you remember the pre-lab and what we did in the lab, mass times change in velocity is change in momentum. This is actually the version of Newton's second law that Newton himself wrote. He said that the force imparted to an object is equal to the rate of change of the object's momentum. How quickly the momentum changes. For those of you in calculus, the derivative of the momentum with respect to time. So Newton never said net force is mass times acceleration. He said net force is equal to the rate of change of momentum. Now notice, if we multiply both sides by the time, we get the impulse change in momentum theorem. This is why I led you to those variables in the pre-lab, because I knew that theoretically Newton predicts that impulse and change in momentum should be equal. And in fact, that's what we found. All of our impulses, regardless of the kind of collision we had, were exactly equal to the change in momentum with a slope of 1, constant of proportionality of 1, so they were equal to one another. So here's our proof. So you don't have to just rely on the experiment. You can also understand this from a theoretical standpoint. Isn't physics wonderful? Experiment and theory matching completely. Now, if you're in class when we do this post-lab, you will see me do a little demo here where we show bouncing versus sticking. So I actually pull out the cart and track and everything you used in the lab, and we use the magnet ends once, and then we use the clay once. And what you'll see there is that an object that bounces has a greater change in momentum. Why does it change its momentum more? Because it has a bigger impulse imparted to it. Well, how do we know that the impulse is bigger besides seeing a bigger spike when we do the demo, or a wider spike actually, more area? Well, it's because something that bounces has a greater change in velocity, and therefore a greater change in momentum, and therefore more impulse. Why does it change its velocity more? Well, this is important that you think of the change in velocity as a vector. Imagine using the magnet ends. The speed out is the same as the speed in because there's no energy dissipated. But that doesn't mean the change in velocity and momentum is zero. That's one of the big errors people make, right? Because you subtract the same thing from itself, you get zero, right? It's a change in velocity, and it always changes in direction when it bounces off. And so they're actually going to end up adding together, not subtracting and canceling. So you got to be a little careful about change in velocity. It's a vector quantity. So actually, if you bounce something, right, rather than hit through it, you'll end up with, rather than hit and stop, you'll end up with a bigger change in momentum. If your car bounced off the tree it was hitting, you'd actually end up with more change in momentum and more damage than you will if it actually hits and stops. That seems kind of weird. Okay, quick little example. Let's say we have a 250 Newton force applied to a 30 kilogram object moving at 25 meters per second to bring it to rest. These are the kinds of problems we've done in the past, except we would do a force diagram, use Newton's second law to find the acceleration, then take that acceleration and use a kinematic equation to figure out things like time. But we don't have to do that. If we think of this applied force as being a collision between what's applying the force and the object, then we can use the impulse change in momentum theorem. Of course, change in momentum is final momentum minus initial momentum. And since the object is coming to rest, the final momentum is 0. Why? Because momentum is mass times velocity. If you don't have any velocity, you don't have any momentum. So plugging in mvi for the initial momentum, solving, we get that the time you would need to apply this force is equal to the negative of the mass times the initial velocity over the force. Now this may throw you for a second, because why do we have the negative here? Well, let's be careful. Velocity and force are vectors. You notice I haven't taken the arrows off. So if you're going to apply a force to an object moving at a velocity to bring it to rest, what direction do you have to push on the object? That's right, you have to push against the motion. So if our velocity is positive, our force has to be negative, and then the negatives cancel. Remember, if you get a negative that doesn't make sense, it's not an opportunity to use an eraser. It's an opportunity to think through the vector nature of what you're doing. Plug those numbers in, you get a nice round 3.0 seconds. Okay, part B. So if here we apply it for 3.0 seconds, 250 Newton force, what if we applied a force for 6 seconds? Twice as long. What would happen to the average force we would need? Now, if you're really thinking, here's our equation, you might not have to actually do any physics other than proportional thinking, of course, understanding the math model. But let's do the math model. Same process, change in momentum is final minus initial. Since it's coming to rest, the final momentum is 0. The initial momentum is mass times initial velocity. Solve for the force. Plug in the numbers, and look what we get. 125 newtons, negative, because you have to push against the velocity. Notice we get half the force. But we had twice the time. You see how that proportionally works? Why? Because think of the change in the momentum. In both cases, you're taking the same mass object and slowing it from 25 meters per second to rest. In other words, you have the exact same change in momentum. But what are you doing? In the second case, you're slowing it down for a longer time. So if your time doubles, you only need half as much force to get the exact same impulse and therefore get the exact same change in momentum. Twice the time requires only half the force. A big force for a small time will give you the same impulse as a big time with a small force. Very graphic, right? So this is proportional thinking. This is the idea behind padded dashboards and seat belts and airbags and collision zones in cars. This is why when you jump from a high place, you don't lock your knees when you land. Right? You bend your knees or even roll. This is why for a soccer player, right, we teach them to draw their foot back as they stop a ball, as they trap a ball. You make your leg a soggy noodle. Right? It's because it increases the time and decreases the force. This is why if you catch something that's thrown at you, you don't hold your hand out and lock your arm and lock your elbow in your wrist unless you want to break them. You cushion it. Because in every one of those cases, airbags, seat belts, crumple zones, pulling back with your hand when you catch something, you are increasing the time of impact, therefore decreasing the force of impact for the exact same change in momentum outcome. So increasing the time decreases the amount of force, and vice versa. If you want to increase the force, you have to decrease the time of impact. All right, so that kind of thing works as well. Now, don't confuse this with what if we want to actually change the momentum more. Again, since I'm the soccer coach, if I'm teaching somebody to shoot the ball and I want them to shoot it and shoot it at a high velocity, we teach them to land on their shooting foot. In order for you to do that, I know it seems kind of weird if you're not a soccer player, but you have to strike through the ball, right, and follow through. as you would say in golf or in football tackle or something. You have to follow through the tackle, follow through the ball. You don't just chop at it, because what you're doing is you're increasing the amount of time that you are in contact. And if you increase the amount of time, the same amount of force will give you a bigger impulse and therefore a bigger change in momentum. So again, be careful about what you're doing here when you're comparing things. Are you trying to get more momentum out, or are you changing the same amount of momentum? Depending on that, you will end up with kind of different proportional thinking. This, of course, will be very much practiced in the next couple of MOPs and worksheets. Some mathematical and some conceptual. So enjoy.